Then next up is Tom Close. There you go. He's going to talk to us about his work, Force Move Games. So we're all really excited for this. So take it away.
Thank you.
And I like the headset, by the way.
Hello?
You're like a celebrity with the headset.
Thanks. I feel like a celebrity. Cool, yeah. So thank you, everyone. It's really great to be here, and it's really great to see so many people who are all interested in like state channels and these off-chain solutions in one place at the same time. So is this going to work? Yeah. So hi, I'm Tom Close. You'll notice that that looks like there's a typo there. There isn't. I was a little bit late to the Twitter game, and so the second O had already gone. So even though I am Tom Close, I'm just Tom Close on Twitter. Like, maybe one day I'll be able to buy that second O. I don't know. Fingers crossed. I am the founder of Magmo, which is a company focused on state channel research and development. So I started looking at state channels and, in fact, Ethereum back in November this year. So I was a little bit late to the Ethereum party too. But I've been working, so I hooked up with L4 and with Jeff and Liam, and they told me everything they knew about state channels, and it was really great. So I've been working pretty closely with them. More recently, I got interested in some slightly different questions, and that's what I'm going to talk about in this talk. Just a little bit more about me before then. So before I started working on state channels, I was working for a startup in San Francisco. So I led the engineering team at a catering startup. And before that, I did a PhD in quantum computing for my sins. So yeah, anyway, this isn't my life story. This is about this paper. So Force Move Games, which is the work that we've been working on the last few months. Show of hands, has anyone read this paper? Oh, that's not bad. Okay, so I mean, like, it definitely isn't the crypto paper of the year, or the month, or even the week, but it is the crypto paper of the next 30 minutes. So you're all here, and I hope that after this talk, you'll either be inspired to go and read this paper, or feel justified in your decision not to. So that's what we're aiming for here. So this is a little bit of an overview of the talk, starting with the introduction, which we've already done. So I'm going to talk about some state channel basics first, just a brief recap of a few of the things you've heard already. I'm then going to talk about why I started working on the Force Move Games framework and what the whole point of it is, how you should think about it, and then finish off with a quick tour of that framework. So in order to go over this state channel basics, we're going to meet a few new friends. So like Alice and Bob have been grossly overworked. Everyone knows them really well, so we're going to meet these new people. And so we've got Jude, we've got Tess, and we've got Matt. And because these are new, I've tried to make it easy for you to remember their names. So can anyone tell me how they're going to remember Matt's name? Yeah, Matt in the Hat. So this is Matt in the Hat. Anyone? Why is this Tess? Tess in the dress. So over there somewhere. And this one's a puzzler. Why is this one Jude? Yeah, Jude's in the nude. So I know this is like probably new to everyone, and it's going to be important throughout the talk. So we're going to have a little test. Who's that? Let's try again. Who's this? And that one? And good, okay. So I think that's the hardest bit of the talk. So now we've got that out of the way, we can move on to the other bits. So I'm going to start with a little overview of state channels. And in particular, the construction of state channels that I'm going to be looking at is the one that they did in the PISA paper. So I think Patrick, okay, this is a bit complicated. It was written up really well in the PISA paper. I think it was initially the same as the one that was introduced in Sprites. Is that right? Patrick's nodding. Good, okay. So in the piece of paper, this is like copied and pasted directly from there. So a state channel allows a group of mutually distrustful parties to execute an arbitrary application amongst themselves while bootstrapping trust from the underlying blockchain. So what does that mean? So you can kind of think of this as executing state transitions off the chain. So we have our 3 new friends. They're starting in this state. I'm just going to abstract the states. We're just going to label that as state number 1. And someone, in this case, Matt. Yeah, well done, that guy. In this case, Matt proposes a new state. So this state is orange. The off-chain transition hasn't yet occurred. And I'm using the fact that Matt's there to signify the fact that Matt has signed that state. So when somebody is standing next to a state, that means they've attested, that is the state I want, I put my signature on it. I've slightly, I guess, glossed over the fact that in the actual construction, there's commands and states. You actually sign the command and the state. But for the purpose of this, you can just think about it as, Matt finds a new state that he wants to move to, and he signs that state, and he sends it round. And then, ideally, what happens is that Jude and Tess decide that they also want to make that state transition, and so they also find that state, and then that state is the new agreed state in that state channel. And this process continues. So maybe somebody else proposes a state this time. In this case, it was Tess, and the other 2 join, and that is how, in the happy, optimistic case, these state transitions are executed off the chain. So what can go wrong here? So let's have a look at this situation. So Jude proposes this new state, and one thing that can happen is that so Tess goes and joins him, and then they wait, and there's nothing from Matt, and maybe he's offline, maybe he doesn't want to do this transition, but he just goes dead completely. So that's one thing that can happen in this scenario. You can fail to execute a state transition by one of your participants blocking. The other thing that can happen is that Matt wants to go somewhere else. So he proposes a different state, and then there's a standoff. So there are these 2 possible futures for this state channel, and neither one of them has been confirmed. Neither one of them can get the 3 signatures that they need for that to be the state. So this is the dispute case. And in this case, this is where the blockchain has to get involved. So you remember from that initial description, they're using the blockchain to bootstrap their security or whatever you want to call it. So what happens in this case is they have these 2 different possible futures, and they submit both their signed states. So everyone submits their signed states to the blockchain. What probably actually happens is one person goes first, and that triggers the dispute process, and then everyone else has some time to submit the other states that they had in the channel, and then the blockchain decides. Somehow it runs this resolution procedure. So it takes the incoming states and the existing signatures, and somehow it decides which transition it wants to do. And then once it's done that, the new transition is accepted off-chain. So the state channel, so we've used this on-chain dispute resolution process to get past the impasse we had off-chain and continue advancing the state. So what we haven't talked about, and in fact, what's often not covered in papers, is how does this resolution function actually make its decision, and what are the possibilities there? So what could this depend on? So it could depend on a number of things, maybe the resolution function is going to go with the majority, or maybe it's going to have some idea of whose turn it is. Maybe Matt always wins. Maybe Matt's the dominant player in that channel, and the resolution function always goes with Matt. So there could be some policy, or maybe state 3A is the dominant state. So like if there's ever a conflict between that state and other states, state 3A always wins. So these are all possibilities. There are also other possibilities, like what does R depend on? Does it just depend on the states, or does it depend on time? Or can it read from the blockchain? Can it like read from like an oracle or something? There are a lot of different possibilities here, and the different possibilities for this resolution function ultimately determine the different behavior you can get from a state channel. So like your state channel transitions, you rely on the fact that if you don't transition, this resolution function is going to sort something out. So like if your resolution function is time dependent, then like you can do time dependent things in your channel, roughly. I'm getting into hand wavily, that's kind of true. So this is like, I guess this is the question that I got interested in. And this is kind of the driving force behind force move games. So that was a brief recap of state channel basics and introducing this concept of this like resolution function and the dispute process. So why force move games? I guess I've discussed a little bit in that last slide the motivation behind this. It's trying to think about like how does the resolution function affect what you can do off-chain and begin to play around with that stuff. So the goal of the force move games framework was to attempt to construct the simplest useful state channel framework capable of supporting multiple applications. So they're already usable like state channel. In fact, any payment channel construct in some way a sort of example of a state channel, or can be thought of as an example of a state channel running a particular application. So we wanted something that was capable of running multiple applications in the same framework. So like you've got this idea that you've got an application developer, you've got a framework. The application developer doesn't have to re-implement the whole framework. They can just write some minimal piece of code that then slots in, and then they can run their games in this framework. So that was the goal. And what we decided to do was restrict the resolution function to being pure and turn-based. So like pure is in the sense of solidity. So pure means that it cannot depend on any state. It cannot read the blockchain. It cannot depend on time. It can only depend on the input states. So like the state you have in the state channel is the only state that you're allowed to use here. And turn-based, I'm going to talk about that in a little bit. So turn-based is this idea, I'm going to talk about that now. So turn-based is this idea that at each stage of your protocol, at each state transition, you have a nominated player whose job it is to make the next, or I mean, who will win in a dispute. So like in this case, Jude has the red arrow. They're going to win any dispute, and so the sensible thing is for them to propose the next state, and then Tess and Matt come along with them because like they know that Jude is going to win if the dispute goes to chain. And then it transitions, so now it's Tess's turn, and like it just like cycles round. And what that means is like if these turns are incrementing the turn number, you can tell from the turn number, you can deduce whose turn it is. So in a very simple case, if you've just got Jude and Tess, all the odd turns are Jude, all the even turns are Tess or something. So you can enforce a very simple rule and your resolution function becomes pretty simple. But that obviously limits what you can do in the state channel. You can't do like arbitrary things anymore. I mean, it's not clear if you could do arbitrary things anyway, but there's definitely a whole lot of things that you could do if you didn't have these restrictions that you now can't do. And so what we did is we set out to build this framework and then see what it could be used for. So like get people to build games on it and stuff, and see how much those restrictions are actually restrictions. I'm just demonstrating the next stage, which is like test this the next one, and then like the state transitions, and it's the next person's turn. Right. I can't remember what this slide was about. Oh yeah, I can. This is great. And there's an interesting optimization that we found here, which is if it's always one person's job to make that transition, you can kind of like get away without having the two other people sign it. And not just, you have to change how the framework works, but like there's no point, you basically just save sending those signatures. So it kind of works like this. So Jude goes first, Tess goes next, and so like each person can just sign the state that it's their right to like make the transition on. So a quick example of a more complicated game that we talk about in our paper and that we've actually already built the smart contract code for and that we're working on an actual like implementation with UI and everything. So this is a 2-player game. We've just got Tess and Matt, and they're going to play rock, paper, scissors here. I don't know if people can read this, it might be too small. But the basic idea of this rock, paper, scissors game is we're going to do like a commit reveal strategy. So Tess proposes the round. In doing that, she increments the turn number, she decides on a stake, and she takes her choice, which is going to be rock. She picks a random salt, and she hashes those together, and she puts that into a state, she signs it, and she sends that to Matt. Matt then decides if he wants to accept the round. In this case, he did. If not, he can just like go back to the resting state. So he's then decided to accept the round. He's added his choice, which is safe to do because Tess is pre-committed to her state in this case. Then the next step is for Tess to reveal her choice. And then finally, once she's revealed her choice, they can update the totals. So this is like, this is how you kind of define a game in this framework. You define the set of states, and you define the allowed transitions between those states. And it's part of designing this game, you have to think through like the economic pressures, so that, for example, in this, if you go into this in detail, if you have a look in the paper, you'll see that in the accept round, they updated the totals as if Matt had won. So I guess something I should talk about very slightly here is when you have this resolution function that is pure and turn-based, you can actually just write the resolution directly into the states because they literally only depend on the current state. And so like that's what we've done here. So like the resolution function becomes very simple. You basically wait. We'll go into that a little bit later. But like here, the resolutions that you would get are written into the state. So each state basically has the amount that each person would get if the game were to stall indefinitely in that state. So hope I've like explained a little bit what the aim of the force move game framework was there. I'm now going to give a quick tour of the framework and how it's set up and talk a little bit about the different parts of it. So this is the diagram that I'm going to be coming back to a couple of times throughout this, and we're going to work around and explain the different pieces and how they fit together. So this line, below the line is things that happen off-chain, and above the line are things that happen on-chain. So you'll notice that we have like, for this game, we have 2 on-chain contracts involved. There's this thing that we call the Adjudicator, which is going to hold the deposit of the players at the beginning of the game. And it's also going to be responsible for enforcing the moves and the rules of the framework. And then we have this game library. Now, the game library is a library and it needs to be deployed once in the world. And it defines the rules of the game. And the adjudicator can call out to the library when it's trying to like figure out whether a turn was valid or not. So the game library can also, you can use that to off-chain check whether people are making valid rules moves or not. And as a quick example, I know you probably won't be able to read this, but this is an example of the game library for a payment channel. So the thing here is like, it's pretty small. Here we're basically checking that each transition maintains the total final balance in that channel, and that you can't unilaterally take funds from your opponent. So if I have a payment channel with Jez and it's my turn, I can give money to him, but I can't take money from him. So as an application developer, you're responsible for writing this contract with a single function called valid transition, which takes two states and says whether that transition was valid or not. So that's the game library part. I'm now going to talk a little bit about the channel and also explain this arrow. So what this arrow means is the channel references the game library, and the moves reference the channel, and the channel also references the players. So what does that actually look like? So this is what these states look like. So when I am making a move, what I'm doing is I'm constructing a state like this. I'm signing it, and I'm broadcasting it to all the players in the game. And this state has three different sections. The first part defines the channel. So things that in the channel, you've got the address of the game library. That's what I meant when I said the channel is pointing to the game library. It's got a nonce to make sure that each of these channels is unique, and that's the responsibility of both players to make sure that these combination of things are unique. And if they don't do that, they're subject to replay attacks. But it's really easy. I mean, it's not really easy. You kind of keep track of it, and you just don't sign anything if somebody's proposing you open a channel with the same details again. And then it's got the addresses of the participants, which defines the participants in the channel. We've got some framework attributes. So we've got the turn number. So the turn number is the version number in other things. So it's telling you how many states are. When we look at the resolution process, you'll see that higher turn numbers win. And then we've got the state type, which is, I won't get into that. There are basically different sections. The framework specifies different sections. So you have a setup phase, and you have a game playing phase, and then you can have a conclusion phase, which allows you to do quick withdrawals. And then we've got game attributes, which are specific to the game being played. So in the rock, paper, scissors example, you've got the state type, you've got the moves, you've got the salt, you've got whatever you need at that stage of the game. So one question is, what happens if this happens? So imagine that Jude first signs state 2A and then signs state 2B. So in the framework, we call this making an alternative move. And in making an alternative move, you give the next opponent the right to choose which move they make. And this is kind of important. You need to cover that in the framework because somebody can always do that. Somebody can always make one move and another move. And it could be the last move, or it could be the first move. But in our case, we decided it should be the person's choice which move to do. So in this case, Tess can choose to go from move 2A to 3. And that's important when we come to the very next step, which I'm just going to quickly do, which is the adjudicator. What does that adjudicator, what functionality does that impose? So the adjudicator has these 5 functions. One is the force move. And the force move, which gives the framework its name, is how you register an on-chain dispute. Basically, what the force move does is it's a way of prompting your opponent to move. So because you don't get those disputes over whose turn it is, and you don't get disputes over what time it is, the sort of disputes you get are the ones which I went at the beginning, which is just somebody doesn't move, somebody goes inactive. And so this is your way of saying, Tess, you said you were at 1 mat, I moved to 2, now you have to move. So with the force move, you have to give the move that person was in, the move that happened next, and then it's on them to provide the next move. And there are a couple of ways they can do that. There are a couple of responses. You can refute. So refuting is proving that person is challenging with old state. So refuting is you challenged me with move 2, but that's an old move. Look, you also signed move 4. So you just show a later move that person signed. And this is interesting because this is the one case where you can prove malicious behavior, and you could potentially punish someone in this circumstance. You can respond with a move, which is kind of the expected thing. So Tess was like, you're at 1, I move to 2. That's like, OK, I move to 3. So in providing that move to the chain, Matt provides exactly the same information that he would have done if he played off-chain. So like Tess now has the signed state that she would have done if it had all been like collaborative off-chain, and that means they can now take this off-chain again. So you can like recover in this framework. You can like prompt someone to move off-chain, and then like when they come back off-chain, you can continue off-chain. And then the final one, and I'm almost done now, is the respond with alternative move. So this is important. It comes back to the right to choose. So like, say Tess challenges Matt. So she's like, you're at 1, I move to 2, now you have to move. And Matt can come back with like, yeah, but you also moved to 2B, and I want to move on from there instead. So like that enforces his right to choose the move he wants to choose. So that was a bit of a whirlwind tour. If you're interested, we have the paper, obviously, and there's also some working code online, which you can have a look at. Thanks for listening.
Awesome, fantastic talk. Is there any questions? Yep, Dimitri rated.
Thank you for an interesting talk. Actually, I have 2 questions. First one, can you open your contract about payment channels you showed just recently? Or it's not possible anymore?
I don't know.
Yeah.
Let me see.
So actually, for me, this approach looks quite dangerous because one party can make a move and others should not agree with him, actually, yeah. And in this particular case, you check that a guy who is making a move doesn't increase his balance, yeah. But it doesn't check, for example, that I moved balance from Matt to Tess if I'm Bob.
Yeah.
Jude.
So this is actually a 2-party. I should have said that. This is a 2-party state channel.
It's 2-party state.
Yeah, we're only checking like the first 2. Yeah, I should have said that was 2-party.
Yeah, it's 2-party.
But in general, you're right.
Okay,
if you had a higher, if you had like 3 parties involved, you'd have to do exactly what you said. You'd have to make sure that you'd have to check that person's balance was decreasing.
The thing that's quite strange that one party can make a move, and the one more question I may be misunderstood. Does a choice who is making the next move depends on the current state?
Yes.
So imagine we have 3 parties, yeah? You, me, and my friends. That's actually, again, me. And me and my friend may create a fork at some point. Yeah, I assign 2 states. I give you 1 state, you make a move. You think that you're on the right chain. And on another fork, we do not show it for you. We make such moves that the next player will be my friend. So not you. And we have make 10 moves, while in your chain we make 5 moves, and our chain is longer and should win.
Yeah. So the way it gets around that is it's dependent on the turn number. And one of the rules of the framework is the turn number must increase by exactly 1. So you and your friend, you can like do however many moves you want between you, but you can't advance the turn by more than 2, because every 3rd state I will need to sign.
So it just depends on the state number, not a state.
Yeah, it depends on the state number and not the state. And that is a limitation. Like, I haven't thought exactly how that's limiting yet, but I think there are some things which that makes difficult. But for a lot of games, it doesn't matter. For a lot of games, and it kind of, like you do need to get everyone's signature anyway. So I don't know. Yeah.
Okay, thank you.
Cool.
Awesome, and we have time for one more question. One more question. Okay, you got catch Tom afterwards anyway, so another round of applause.
Thank you.
Awesome, good job. I like Tez the best.